Section 1.3, more about limits. The first part of the section, if you look in the textbook, it talks about all the properties of limits. And I've written some of them down here for you. The limit, if you're adding some things, some functions, or subtracting, just means you need to take the limit of each piece and then add or subtract those answers. If you're multiplying, you can take the limit of each of the factors and multiply the answers. Same thing with division. The limit of the quotient is the quotient of the limits. The limit of the product is the product of the limits. The limit of the sum is the sum of the limits, right? This looks complicated, but when you put it into practice, you're really just plugging numbers in and chugging out the answers. Notice that if you have some function raised to a power and you're taking the limit of that, you just take the limit of the function and raise that answer to the power. All of these things are things that you will do intuitively because you've learned to do them already. You just didn't realize what you were doing. The limit as x approaches any number of a constant is always going to be that constant because a constant is not dependent on the value of x. So it doesn't matter what x is approaching, a constant equals a constant. And the limit as x approaches a value of x is that value that x is approaching. You take this guy right here and this guy right here, and you use it in the context of all of these, and you've got everything that you need just about. Okay, some examples. What those properties tell you you can do is that if you have the limit of something, you just plug in the value, chug out the answer, boom, you're done, right? As long as you're not dividing by 0, you are good. Now we saw in the first video that if you plug in those values and you get 0 over 0, it's not just undefined, it's indeterminate. So when you get that, you know that plugging in x equals some number and you get 0 as an answer means that x minus that number was a factor. And if you get 0 on both the top and the bottom, then it was a factor of the top and the bottom. So you factor it out, cancel it, and then you plug in the number again. So for example, if I plug the 0 into this guy right here, I get 0 minus 0 and 0 on the bottom. So I know that I can factor x minus 0, or plain old x, out of both the top and the bottom. So I factor it out of the top, it's there on the bottom, bang, bang, let me write that, bang, cancel, then plug that value that x is approaching into the bit that's left, and you get your answer. Another example, this guy right here, we're plugging a 1 in, square root of 1 is 1, minus 1 is 0. 1 minus 1 is 0. Now I can't really factor this. I could factor this as the square root of x plus 1 and the square root of x minus 1, but that's not right there in your face intuitive, right? So if you see a problem like this, especially if it has a root in it, multiply by the conjugate. If I multiply by the conjugate on the top and multiply by the exact same thing on the bottom, the part on the top gets FOILed out. You multiply these two out, leave the bottom factored just to see what happens, because it was the conjugate of the top that you multiplied by, right? So that's what you're going to FOIL. And look, when I FOIL this guy out, I get x minus 1, which is going to cancel with the x minus 1 on the bottom, which leaves me the root of x plus 1 in the bottom. And now I can plug the 1 in. I get 1 plus 1, and I end up with 1 over 2. So try some of those in the homework. You'll see that if you have a root, you just multiply by the conjugate. Simplify it out. You don't have to multiply everything. Only multiply the thing that you've got the conjugates of. And you'll see that stuff cancels. And you know it's going to cancel because you had 0 over 0 in the first place. Okay, here's another example, and yes, you will be having trig functions. If the limit as x goes to pi over 2 of plain old x times the sine of this, plug in the pi over 2 here, plug in the pi over 2 here, we get this. Now the sine of pi over 2 is 1. You better know that without even having to think about it. So we have pi over 2 times 1 equals pi over 2. Now look at this guy. I plug the 0 in here and the 0 in here, but what's the sign of 0? The sign of 0 is 0. I get 0 over 0. So what are you going to do in this case? You can't, oh, hello. You cannot cancel right here. Some of you tried to do that, or you thought, why doesn't she just, yeah, this x is not a factor. It is the argument of the sine function. So you better watch your step here. The sine right here and that x can never be separated. That x is being operated on by the function sine. So this is not multiplication, which means you cannot cancel. You got to come up with something else, okay? So there's no conjugate to multiply by, so I can't use that little trick. So what do? Let's look in the textbook. Theorem 1.9 gives you two special limits. You have this limit right here, where you have the sine of something divided by the exact same something, and these two somethings both go to 0. When you get this limit, it comes out to be 1. I know, crazy, right? And as a consequence of this right here, and I'll show you how that works in a minute, you get this guy right here. If we plug theta equals 0 in right here, cosine of 0 is 1. That's 1 minus 1, 0. And that's 0. 0 over 0. So we can't just plug and chug. We have to know that this is true. And we'll prove it on the next couple of pages. Now, number 1, this guy, which is what the other one is based on, is found by using something called the squeeze theorem. The squeeze theorem is theorem 1.8 in your book. And let's look at what happens when you use the squeeze theorem. Okay, let's say I have 3 functions, and they all agree at that point right there. It doesn't have to be 0. They all agree at some point. And you notice that I have one function that is always greater than my f of x, and one function that is always less than my f of x. Now, it doesn't have to be true everywhere, but in the general neighborhood of the thing that you're taking the limit of, it's right there. And notice that for this problem, what we're looking for is the limit, in this case, as x approaches 0 of f of x. All right? And if we can't find it, it's something like sine of x over x from the previous page. We can't find it, so we have to use another tool. So what we've done is we found a different function that touches my graph, but is otherwise always above, and a function that touches there, but is otherwise always below. Notice that g of x, the limit as x approaches 0 is 0. And for the red one, sorry, that's an H, isn't it? Hold the phone. The red one is H of, H of x. Notice that the limit as x goes to 0 of h of x is going to 0 as well. So both of these functions are going to 0, and one function is always smaller, one function is always larger. My guy is always in between. But if this is going to 0 and this is going to 0, then this guy in the middle gets squeezed. And he gets squeezed to be a 0. And that's how you use the squeeze theorem to show that your limit also is 0. Okay? The squeeze theorem is 1.8. And that special limit with the sine of x over x is theorem 1.9. I want you to look in the book and you can see the proof of the theorem 1.9 using the squeeze theorem in your book. It's pretty cool. We just don't have the space or time to do it right now. So look at that in the textbook. And I only think there's 1 or 2 problems, maybe only 1, that talk about the squeeze theorem. And it's pretty straightforward. Okay, so how do we use this special limit? Well, we had the limit of sine of x over x goes to 1 when x goes to 0, right? So now look at this. This has to be the same as this, and they both have to go to 0 for me to be able to use that theorem. So the bottom has to be a 2x to match this angle. So I just multiply the top and the bottom by 2. This 2 is going to be a multiplier out front. This 2 is going to multiply the x on the bottom. Now you see I have the same angle and number on the bottom. And when x goes to 0, this goes to 0 and this goes to 0. So I factor this 2 out in front, and I look at this limit right here. I use my special limit theorem, and this guy goes to 1. So he's a 1. It's multiplied by a 2. My answer is 2. Another example, look at this guy right here. Now in this case, the argument of my sine and my denominator are exactly the same thing. But do they go to 0? Well, if x goes to 1, then this goes to 0 and this goes to 0. They're exactly the same. I don't have to do anything to it. I know that that goes to 1. And here is the reasoning behind that right here. What if we have that upside down? Well, remember all your properties. This fraction upside down is 1 over, right? So now I look at the limit of the 1 divided by this function, and I remember my properties. It's the limit as x goes to 1 of the top, 0, sorry, of the top, which is just 1, and the limit of the bottom. Now the 1 keeps going. Here's my top. The limit as x goes to 0 of sine x over x gives me a 1. 1 over 1 is 1. So you can look at this guy right here and just say, well, that's 1 upside down, which is, again, just a 1. All right, one more. This is the second special limit that we had. If we plug the 0 in, we get 0 over 0. So I'm going to show you how you can use the first property or the first theorem to get this second theorem. I'm going to take my original argument here inside my limit. I'm going to multiply by this trigonometric conjugate. So I had 1 minus cosine, I multiply by 1 cosine. If I do it to the top, I have to do it to the bottom. Now I'm going to leave the bottom factored and multiply out the top. You see I get 1 minus cosine squared. Well, we know our trig identities, 1 minus cosine squared is sine squared. So I have a product in the denominator, and I have a product in the numerator, sine times sine. So I'm going to choose to take one of those signs and put it with the x, and the other sign and put it with the 1 plus cosine in the denominator. So remember, the limit of the product is the products of the limits. So I can take the limit of this and the limit of this and multiply my answers. So this guy right here is just 1 right here. Now I take the limit of this, I'm just plugging 0 in. I get a sine of 0 on the top, 1 plus the cosine of 0 on the bottom. That's 0, sorry. Cosine of 0 on the bottom. And you see cosine of 0 is 1. The bottom here is 1 plus 1, which gives me a 2. But 0 divided by 2 is still 0, and 1 times 0 is 0. And that's where that special limit comes from. The limit as x goes to 0 of 1 minus cosine of x over x. These match. They both go to 0. You get 0 for your answer. And you're using this guy going to 1 in the process of finding that. All right, your homework for this section is 1.3, 5 through 91, do every other odd. So it's every fourth odd problem.